In this video, I'm going to talk about networks and flows. This is a special type of graph which is used in many applications like communication networks, assignment, scheduling problems, logistics systems like transportation of goods and optimization problems related to that. Pipe networks like water networks, food networks, and even electric grid. So what is a network? A network is a connected, directed graph. In a network, there's at least one source. You see the source X here in this example. And then at least one sink. So in our very simple example here, we have one source node where all edges are leaving this node. You can see the two arcs here. And then there's one sink node or a kind of a destination node where all edges incident to node Y are incoming edges. Let's define the flow. A flow for network N associates a non-negative integer FUV. So each edge is assigned an integer value. It can be a 0 or a positive value. That's what non-negative means. There's also this rule here for all vertices of the network other than the source and the destination. This equation has to hold. What does it mean? For any node that is not a source or destination or the sink, all incoming flow, the total of all incoming flows, should be equal to the total of outgoing flows. And this equation here is also called conservation of flow. And that is valid in each vertex except the source and the destination. There is also one other value that is associated with each edge in a network, and that's called the capacity. A network is basically a model for the flow of material leaving a single departure point and arriving at a single destination. That's why we have a source and sink nodes. In practice, there is an upper bound on the possible flow along any edge. Each edge has a capacity. You can imagine it as a pipe. Say, for example, if it's a water pipe, the amount of water you can push through that pipe is bounded by a value. And that capacity represents that value. In practice, in all applications, there's such limit. So the capacity on the edges makes sense. So we will represent this with CUV. The edge starting at U and ending at V will have a capacity C. So for each edge, the relation between the flow value and the capacity is always like this. The flow will be between 0 and the capacity. Flow on an edge cannot exceed the capacity of the edge. Here's an example. This is the same graph. We have seen a few slides before this. And here are some values assigned to each edge. You can see that there are two values assigned from node X to node 1 on this edge. For example, you see the values are 1 and 2, two different integer values, and 1 represents the flow on this edge, and 2 represents the capacity. You can see that each of the edges of this network are assigned some values. And in all of these edges, you can see that this inequality always holds. The maximum flow on any edge can be only equal to the capacity of that edge. Okay, we have seen the definition of cut in our previous lessons. Here, we will define the cut for a network. This is slightly different than what we have seen before. A cut on a network is a cut set of the underlying graph. But then we have this rule that the cut will separate a node set P from the other node set P bar, where P contains the source and P bar contains the destination. So any cut you can create here, a cut from here to here, for example, or a cut here, are valid cuts based on this definition. Here's an example. The dashed red line here shows you a cut, and that cut contains 3 edges. 2 of them are from the source side to the destination side, x2 and 1, 3, and the other edge is on the reverse side. Okay, once we define a cut, we can then talk about the capacity of the cut. The capacity of the cut is denoted by K bar, and it is equal to the sum of the capacities of the edges in the cut. But there is a catch here. We do not just simply sum all the capacities of all edges in the cut. What we do is we select those edges such that the starting node belongs to set P and the ending node of the edge belongs to set P bar. This should be P bar. And we only add the capacities of the, such edges that obey this rule here. So if we examine this example, again, X is source, Y is sink or destination. So this side of the graph, X and 1, these 2 nodes belong to P, and 2, 3, and Y belong to P bar. 2 different subsets of the vertex set. And by definition, the capacity of this cut is only the sum of this capacity of this edge, 1, 3, which is 2, and the capacity of this edge, x2, which is also 2. So the total capacity of this cut is equal to 4, not 5. And then another definition, the value of a flow. The value of a flow for a network is the net flow leaving the source X. You can also find this value on several cuts. Based on this theorem, for an arbitrary cut of the network N, the value of the flow is given by this formula here. You choose any cut on the network, and then you look at the direction of the edges. If the direction of the edges, the edge of any edge in the cut is from the source side to the destination side, that adds up to form the total flow value, but then we subtract the flows on the reverse edges. So flow from P to P bar minus flow from P bar to P gives you the net flow from source to destination. And here are several examples. Let's look at the red cut here. the net flow from X to the other side of the network is 1 plus 2. It's 3. Let's look at the blue curve here. Cut represented by this blue curve. There are 1, 2, 3, 4 edges on that cut. But remember, we have to add the flow from source to destination, source side to the destination side. So there will be a value of 2 and a value of 1 added. So those are 3 in total, and then this one 2, another 1, 4. But then there's a reverse edge which has a flow of 1 minus 1. The total flow of this cut is again still equal to 3. We have a corollary from the previous theorems that says the value of the flow for any network cannot exceed the capacity of any cut. Remember that on the same network we have seen a cut of value of 4, the capacity was 4, and you can find some other cuts with different capacities. The smallest of all these capacities puts a limit of the maximum flow that you can create in this network.